We go from Charles Bennett from IBM Research, one of the pioneers of quantum cryptography, among other things, whom I said was both a physicist and a computer scientist. And we go to Adi Stern, who is younger. Entangled state. We go to Adi Stern, who is younger and is only a physicist for now. And one of the reasons for inviting him to this conference is to try to get him to be also a computer scientist. And he is one of the best speakers that I've ever heard, as I think you will see in a few minutes. He's at the Weizmann Institute, and he is a newly elected member of our academy here, I think last year. And I'm going to ask him to come and talk to us about physics and quantum cryptography.
So thank you very much for this introduction. I'm honored to be speaking in a computer science conference. I didn't know it's a conversion attempt. And I'm particularly honored to be speaking after Charlie Bennett, one of the pioneers of this interface of quantum physics and computation. So I have a kind of an ambitious program. I'd like to tell you about topological physics and quantum computation. And so my plan is to explain first. There's going to be a lot of physics here, but don't worry. So I'll talk about what topological states of matter are, and in particular, what's the quantum Hall effect. And I'll explain this. Then I'll go even more complicated for something called non-abelian states, and I'll explain how they may be tools for doing quantum computation that's relatively immune to decoherence. So since I'm going to say it's going to be relatively immune to decoherence, I'll also explain what decoherence is. And I'll explain why non-abelian states minimize it. And then, being a physicist, I'll have to come to real life. Do you actually need a computer, a microphone for me?
For the recording.
Oh, recording, okay.
Okay, whatever you say now is going to be classical.
Yeah. So I'll tell you what how non-abelian states may help us in avoiding decoherence, which is the main obstacle we have on the way for quantum computation. And last, as being a physicist, I'll go down to real life and tell you where we stand now in attempts to actually realize in a laboratory the ideas that I talked about before. Now, there's going to be a very important device that I'm going to use in the entire talk, and I recommend you to use it as well. And this is a carpet, a rug, and I'm going to sweep under the rug lots and lots and lots of details and concepts and important parts. But, it's a limited time. So the first thing I'm going to talk about is the quantum Hall effect. Now, in effect, what's the Hall effect? The Hall effect is a situation where we have a two-dimensional system where a current is flowing, an electric current is flowing from the left to the right, let's say, and there's a magnetic field acting on the current. Now, what's a magnetic field? Let me tell you the only thing you need to know about it. And this is that if you go straight and you are under the effect of a magnetic field, the magnetic field is trying to push you sideways. Now, whether it tries to push you to the left or to the right, that's not important to us. As you know, left and right are not easy to distinguish. So it's not really important. But it tries to push you sideways. And when I prepared that slide, I think I got the side. I hope I got the side right. In any case, because the magnetic field tries to push the current sideways, charges accumulate on the side of the device, and there's an electric field or a voltage developing between the two sides. Now that's something you learn in high school in some cases or in BSc of physics. But the point is, a force is applied by the magnetic field, which is linear in the magnetic field, and therefore an electric field develops that cancels this force. So you'd expect it to be linear. You'd expect this electric field to be linear in the magnetic field as well. Okay, now we can measure that electric field. We actually measure voltage and we divide it by the current to get the resistance. The important thing is we expect it to be linear in the magnetic field. Okay, and it was for quite a few decades. From late 19th century to late 20th century, it was linear. And not only that, now you see the experiment, and what you see is this voltage or the resistance, the voltage perpendicular to the direction that the current is flowing. You see this one as a function of the magnetic field. This is the red line. There's also a green line, but people don't like to talk about it. That's a political reference, but it's also a quote from Winnie the Pooh. I'll quote it fully if you ask me in the break. In any case, the red line is what we were interested in, and you see it starts linear in the magnetic field. But then a few things happen. First of all, steps develop, right? You see these steps. And in the step, it seems that instead of the proportionality that we expect, we get a straight line, right? By the way, do I block your sight? No, you're fine. So you see that it looks like a straight line. Now, it doesn't look like the straight line. It's probably the straightest line you've ever seen. From here to here, the magnetic field changes by about 30 or 40%. The voltage perpendicular to the current, or what's called the Hall resistivity, the Hall resistivity does not change, not by 1%, not by a tenth of a percent, not by a hundredth of a percent. It does not change. It is kept constant to 1 part in 10 to the 9. That's one of the most precise phenomena known in physics. And you see, it really doesn't change. Not only that, you repeat the experiment in a different device using a different material, a different graduate student, a different measuring. You change everything. And indeed, the beginning of the step will change. The end of the step will change. You know, what magnetic field it starts and end will change. The value of the resistivity on the step will be the same at every experiment, 1 part in 10 to the 9. Not only that, the ratio between this number and this number will be 2.00000. That's an amazing observation. Now, the value of the steps is always 25,800 something or other, dot various other numbers divided by nu, where nu is either an integer, but you know, a simple integer like 1, 2, 3 up to 12, something like, you know, a kid of the age of 4 or 3 counts, or a simple fraction, but again 1/3, 2/5, simple. Those are the values. Now, there are many questions this brings up, but the first and obvious one is, what is this number? This, by the way, measured in units of ohm. So what's this number, 25,000 ohms and whatever? Turns out it's the ratio of Planck's constant, the constant that defines quantum mechanics, divided by the electric charge squared. Now, this is just unbelievable, and it's true, but it's unbelievable. You know, this universe has four universal constants. The Planck constant, the electric charge, the speed of light, and the constant of gravity. And you measure the ratio of these fundamental constants to 1 part in 10 to the 9 using this device, using a device that's as dirty and as full of details as this one. As I said, you can replace you know, these wires by maybe better looking wires. You can replace this material, which turns out to be gallium arsenide, by silicon, by graphene, by silicon germanium, by one of about 30 or 40 materials. You can replace the shape from being that shape to being slightly different, and the answer will be the same. The ratio of the Planck's constant to the electric charge squared. This is about what, I think 30 years old, this observation, 30 or 40, somewhere around there. So this is again this data, and just to focus on what exactly is going to be important to us. In fact, what's going to be important to us is this number nu that I mentioned before. And this nu will frequently, in the interesting cases, actually not in the cases shown in this plot, but in cases that you see in higher magnetic fields, this will be a fractional number. So it's always rational, no reference to square roots of 2 and stuff. It's always rational, and P and Q are small numbers. And Q is frequently an odd number, but not always. Now, this is the experimental observation. Now, I'm not going to go deep into this because I'd like to relate it to the topic of the session of quantum computation. But I'd like to tell you that if you use these experimental results, which are beyond doubt, they were produced many, many times, no one cheats. You use basic principles of physics, like conservation of energy, conservation of charge, things we are not going to give up just because some experiment came out. And you use just, plain logical reasoning and a piece of paper, not more than one. You can come out with a few revolutionary conclusions that you just simply cannot, without understanding anything, you just have to accept. And I'd like to mention 2 of them. That conclusion is basically a Nobel Prize winning conclusion for Bob Laughlin from Stanford. And that's the observation that the fact that you see this fractional number nu implies, unavoidably, that the system that is made all of it is made of single electrons. Only, electrons come in single units. This system will have what we call quasi-particles, which are, like particles, but quasi-particles. Quasi-particles whose charge is a fraction of the charge of the electron. So somehow, having a system where each component has the same charge, somehow it may mimic behavior of a charge that's a fraction of that fundamental charge. Not only that, but if you look at the spectrum, and I'll remind you in a second what do I mean by a spectrum. If you look at the spectrum of what possible energies can this system have, the system that I showed you, this piece of semiconductor with all this dirty stuff, or at least something very close to this, if you look at the energies that this system may have, you will find that the lowest energy, which we call the ground state energy, will be degenerate. There will be several ground states with the same energy. Now I'm not going to show to you how this is an unavoidable conclusion. This will take about twice as long as my talk, not a full course. But I am going to tell you a little bit about this degeneracy and what it means. So first of all, how do you get to it? This is a famous argument called TKNN in the jargon, Thouless, Komoto, Nightingale, and Denice. And it's based on thinking about a geometry that's slightly different from the one I mentioned to you, from the one I showed to you. And this is the geometry of a torus. You put this system on a torus. Now, I'm a theorist, as you know. Many of my friends are experimentalists, and one of them said dryly, come back when it's planar. This is not something you can do in a lab, but as a thought experiment you can think about it. A torus has 2 holes. You put magnetic fields in the 2 holes, and you call them phi 1 and phi 2, and you can show that the quantity that you measure, this number nu, is some integral of some derivatives of the ground state with respect to the 2 fluxes. You take a scalar products. All this really is not important. What is important is that you can show that this number, this is an exercise that takes, I teach it in about 2 meetings. You can show that this number is an integer number. It's a topological invariant. It's something that cannot change its value by that does not change its value if you change the system slightly. You need to have the system go through a major change in order for that integer number to change its value. Now that's good news and bad news. Good news because it tells you that you have a quantized number. Bad news because it's an integer, and I told you that the experiment shows that this nu can be a fraction. So you go back to the proof. I'm telling you how I teach it. You prove that it must be an integer. Then you go back to the proof and ask yourself, what assumption did I make that must be violated? And the assumption is the assumption of the ground state, this psi, the ground state being non-degenerate. So you assume that it's non-degenerate. This assumption is wrong. Now let me explain what this issue of degeneracy. So in quantum mechanics, a system has a spectrum. It has a set of possible states at which it can be. The most famous spectrum is the one that Niels Bohr basically used to give birth to quantum theory. And this is the spectrum of the hydrogen atom. So the hydrogen atom has a ground state, and then it has excited states, and you may remember from your chemistry high school classes, there are shells, and one shell has 2 states, and another has 8, and another, I think 18 also appeared there. In any case, there are energies which are allowed, and then there are the number of possible states that each of these energy can have. That's called the degeneracy. This is at the end of the day, you have a matrix, you diagonalize it, the energies are the eigenvalues, and how many degenerate eigenvalues exist. That's the issue of degeneracy of the states. Now, in the hydrogen atom, as I said, there are these 2, 8, 8, 18 or whatever, degeneracies. They come out of a symmetry, out of the fact that the hydrogen atom lives, at least in Bohr's mind or lab, it lived isolated from the rest of the world. So there's a spherical symmetry of the system. So whatever state you have, if you rotate a little bit, you'll get another state that is degenerate in energy because there's nothing changed because it's all spherically symmetric. Real life, of course, is not in Bohr's mind or thought experiment, and the hydrogen atoms interact with other atoms and therefore lose this degeneracy. They don't have the symmetry, and the degenerate states split. The important aspect here is in this topological world is that there's a degeneracy that's protected by topology. I read it like Hebrew, from right to left. There's a degeneracy that's protected by topology, meaning in a quantum Hall system, just out of the mere observation of the fractional value of nu, we can conclude that the ground state of the system, when you put it on a torus, I'll get rid of that requirement in a minute. When you put it on a torus, the ground state will be degenerate, and this degeneracy will be topologically stable, meaning if you change the system a little bit by having your cell phone operating while you do the experiment, or moving one of these wires that you saw in the experimental sample, moving a little bit. Any small changes will not split the degeneracy. It is not a degeneracy that comes out of a symmetry, and therefore it does not depend on any symmetry. It's stable. So the spectrum of a quantum Hall system, or fractional quantum Hall system, will have several degenerate ground states, then an energy gap. The energy gap is also an experimental finding related to that green line, which I swept under the rug with a joke. And then there's a continuum. So a few degenerate ground states separated by an energy gap to a continuum of states we don't want to know about. The idea of topological quantum computation is, let's use this set of topologically protected ground state as our computational subspace. Those will be the states to which we will encode the qubits and on which we will carry out the manipulations, changing the states of the qubits and all that. The good thing about that clock there, it doesn't work. So I don't know how much time. So how much time do I have?
Keep going.
Okay, good. Thanks. So this is the topological invariant. Does it have a name? Yossi, does it have a name?
Yes.
What's the name?
You know.
Well, you go.
It's a Chan number. It's the first Chan number.
Okay, yeah.
There is a
Yeah,
line.
right. So, but the name I prefer is it's the whole conductivity. That's the story. We have a set of degenerate ground states. We are going to use them to encode the information and use something to manipulate. I have to tell you what this something is. So I have to say, this is a combination of good news and bad news. The good news is this degeneracy is very robust. It does not respond to bad perturbations, that we don't want. The cell phone in your pocket, the noise in the lab, and so on. But that piece of good news is also a bad news in a way, because the way we deal with the physical systems is we perturb them and see how they react. If this system will not react to our perturbation, how are we going to, encode information into it, extract information from it, and so on? So that's something I'll have to explain to you. But first, I promised you to get rid of this torus. The torus is a non-starter experimentally. And that's where this idea of non-abelian quantum Hall states come in. Non-abelian quantum Hall states are quantum Hall states in which the degeneracy does not come out of being on a compact geometry with no edges like on a torus, but comes out of having in the system these fractionally charged quasi-particles, these excitations which I mentioned to you, which we have to accept exist and have a fractional charge. Okay, so in some cases, for some quantum Hall states, not all of them, for the non-abelian ones, I'll explain the name, by the way, in a few minutes, the existence of these quasi-particles in the plane will give rise to a degeneracy of the ground state. And in fact, the degeneracy is exponential in the number of these quasi-particles. Now, who encodes the information? Usually, if there are states which are degenerate and are different from one another, there should be some degree of freedom that encodes that describe them. And in Charlie Bennett's talk, it was the polarization of the photon. It could have been like that or like that. It was an internal degree of freedom of the photon. Here also, the information is encoded in internal degrees of freedom. But the internal degrees of freedom, and that's a major difference from this and the photons and the trapped ions and the superconducting qubits and all the other realizations. Here, the internal degrees of freedom to which you encode the information are non-local, meaning the information is not here and is not here. If you want to measure it, you need to bring the two quasi-particles close to one another. As long as you don't, as long as they are far away from one another, you cannot measure this information. And if you cannot, also the environment cannot, and there's no decoherence. So that's the world of topological quantum computation. A set of degenerate ground states separated by an energy gap, we assume the energy gap to be very large. We wish this assumption was correct, but I'll say a few things about that at the end. But a set of degenerate ground states, and those are going to be our qubits. Now I have to say, if you are familiar with this type of physical systems, this seems to be also a problem, because how are we going to manipulate the qubit? Let's say we put the system in one ground state, and that ground state is we refer to as the bit being 0. Or we put it in a superposition of this ground state where the bit is 0 and this ground state which we refer to as the bit being 1. So we have a superposition of the bit being 0 and the bit being 1. Now that's the story of quantum computation, right? The entire idea is to have a superposition of 0 and 1 where alpha and beta are complex numbers. The modulo squared, the sum of the modulo squared is 1, but there's a relative phase between them. Now we frequently draw or describe this alpha and beta as coordinates on what's known as the Bloch sphere. So it's a point on the Bloch sphere, and doing quantum computation means you know how to move your point on the sphere controllably and precisely from one point to another point. Now, how do you do that usually? How do you do that in any non-topological system? You have an energy difference, and you use the fact that as time goes by, each of these two states get a different phase which is linear in its energy. So this one gets a phase epsilon 0, its energy, times t, and this one has an energy epsilon 1, so it gets a phase epsilon 1 times t. And then if you want to change the relative phase by pi over 2, pi over 3, or any other number that you wish, you tune this product of the energy times the time in a proper way. Now, but here I told you there's no energy difference. These two phases will be the same because the energies are the same. So we need a new way to manipulate bits. And indeed, in a topological quantum computer, there is a new way. And that's what I'll describe to you now. Excuse me. So this is our system. It has these particles, these quasi-particles, these excitations which are so unique to this system. And it has a set of ground states. 1 to as I said, exponentially large number of ground states. And those ground states all depend as parameters, the wave functions depend as parameters on the positions of these quasi-particles. Now, what we want to do is to find a way without changing energies, because we know the energies are all going to be the same. Without changing energies, we want to be able to go from one ground state to another. It turns out the way to do that is to do something called braiding. Now, am I the right person to talk about braids? I'm not sure. But this is what this trick is doing. And this is the braiding is the braiding of the word lines, of the positions of the quasi-particles as time moves on. So, I take this quasi-particle and move it to the position of this one, and I take this one and move it to the original position of the first. When I do that, the system evolves in time in such a way that it stays in the ground state subspace. So it stays in a superposition of ground states. But which ground state exactly it gets to depends, it turns out, on this trajectory that I'm doing. So the operation of interchanging two quasi-particles or braiding two quasi-particles, this operation applies a unitary transformation on the system that takes it from one ground state, from a superposition of ground states, to another ground state or superposition of ground state. Now, a unitary transformation is a matrix. Matrices do not commute when you multiply them. Therefore, if you first interchange 1 and 2, and then 2 and 3, or if you first interchange 2 and 3, and then 1 and 2, the answer will be different. The outcome, the final state will be different because you multiply matrices, and that's the name, that's the origin of the name non-abelian, non-commutative. So the way we manipulate qubits will be by interchanging quasi-particles. But now comes the great promise of this story. The great promise is that the final outcome, the unitary transformation that you apply, does not depend on the details of this interchange. You know, if I do it like that, or I do it like that, I'm going to get the same final state. The only thing that matters is the topology of the trajectories. So here you see the topology of this trajectory. I had 1, 2, and 3. I first interchanged 2 and 3, then I interchanged 1 and 3, then I interchanged whatever, 2 and 1, and I ended up with this braiding process, and this will determine the unitary transformation. The details, the geometry, and the dynamics of the way I do that, do I do it, you know, with the velocity going like that or like that, doesn't matter. There are caveats here, but you remember the rag. It's all in the topology. And this, for a quantum computer, is a great promise. Because the main problem of a quantum computer is the noise. Is noise, decoherence. All this will be avoided here because you don't care whether there's noise in the way you perform the unitary transformation or the manipulation. Now, a quantum computer needs to fight decoherence, to fight noise. It also needs to have a universal set of gates. That is probably a statement that's understood better by any single member of the audience compared to me. But that's what the point of you need a universal set of gates, otherwise you will not be able to carry out all the unitary transformation that you may call the algorithm that you want to carry out. Does this constitute a universal set of gates? The answer, it depends. Depends what non-abelian state you are looking at. And as I don't know if Moore's law is going to hold for a long time, but Murphy's law will. And as you can imagine, the more universal a state is, the harder it is to actually realize it in an experiment. Maybe I'll ask again about time, because this will make me decide.
Just type this and add 1.
Ah, okay, thanks. To the left of the digit. Okay, so everything I told you about was about non-abelian quantum Hall states. There are many examples now for topological states of matter. A smaller subset are sets which are states which in principle may be used for topological quantum computation, meaning states which have a degenerate ground state. The second example which I want to mention is that of what's known as topological superconductor, and that's you know, superconductors are materials that carry current without getting heated. It's not everyday life, but it's kind of everyday knowledge. I won't get into details. I'll just tell you the mathematics of it, because it explains what holds it, what gives it a topological protection, what gives it a topological stability. So for non-physicists, a superconductor is something that's described by a matrix. And if you want to know the energy states of that of the superconductor, you need to diagonalize that matrix. Now, if you diagonalize it, and you look at the zero eigenvalues, how many zero eigenvalues tell you how many ground states you have. It's not a one-to-one relation. There's a power there, but that's what, there's an exponent actually, but that's what you need. You need zero energy eigenvalues. Now, that's the matrix. You don't care what all these letters mean. What you care are two things. First, it has an even dimension, and that's easy to see, because this and this are the same matrix up to transpose. So this has an even dimension, which means it has an even number of eigenvalues. Then another thing which I could show you if I had 10 more minutes is that the eigenvalues comes in pairs of positive and negative. Now you combine these two observations and you have to conclude that if the matrix is even dimensional and the eigenvalues come in pairs of plus and minus, the number of zero energy eigenvalues must be even, right? Now, otherwise I'll have to violate one of these two. Now, 0 is an even number, but not an interesting one. So let's go to the next one, which is 2. So the number of zero energy eigenvalues, or zero eigenvalues for that matrix will be 2. Now, the eigenvector corresponding to each eigenvalue acts in space. It's an operator. I won't get into details, but it has a position. So if I have two zero eigenvalues, one localized here and one localized here, each one of them will be stable. Because if I come to this one and try to move it away from 0, I cannot, because if it moves away from 0, the other guy will remain alone, will remain a single one. And then I'll have an odd number of zero eigenvalues, and that's not allowed. So those two, as long as they are far away from one another, are stable. And that's the source of the stability, at least for the superconductors. Now, to quickly talk about phase coherence, the crucial point, so actually, okay, the previous talk already covered a bit of this issue of phase coherence. You need the environment not to measure you. And in this case, the distribution of the information over non-local degrees of freedom tells you that you cannot measure, neither you can nor the environment can measure the information of that set of qubits without getting them close together. So as long as you keep them far away from one another, you're safe. So in my minute and a half, I'll skip this. In my minute and a half that are remaining, I'll tell you about real life. So these ideas of topological quantum computation originated in the early 2000s. You saw names here and there. I guess Alexei Kitaev is the name I have to mention in this context. He was the originator of this idea. And about 10 years ago, a big experimental effort started, spearheaded by Microsoft, by what's known as Station Q, Project Q. I was part of it for about the last 10 years. And that project tried first the quantum Hall and now more the superconducting avenue, trying to look at wires, superconducting wires, and looking at zero modes along the wire. Now, there are many experimental knobs you can use for realizing this: magnetic fields, gate voltages, charging energies, and so on and so forth. The first thing you want to see is that indeed, that there will be signatures, experimental signatures for the ground state being degenerate, for having many states which are degenerate. That's the first thing you want to see. That was, I shouldn't say it, and I'm being recorded, but I want to say surprisingly easy. It wasn't easy, but it didn't take very long. It took about a year or two. And what you see here is not the first experiment, but a later one. And this peak at 0 voltage, what you see here, this is a superconducting wire. Those are gates where you tune densities, various things. In any case, the fact that you see this stable peak at 0 voltage is an indication that there is a ground state degeneracy. Is it the only explanation for this? There may be alternative explanations. I think that it's getting safer and safer to say, yes, we know that these superconducting wires have a set of degenerate ground states. Now we want to manipulate them. We want to braid. We want to start in one ground state and end in a different ground state. That, I think I can safely say, has proven to be very difficult. That's something that's being attempted now in various labs around the world. Copenhagen, Delft, NYU, Santa Barbara, various other places. And it seems that there's a difficulty associated basically with materials quality. That's not something to talk about in a computer science conference, so I won't. I'll just summarize. And my summary has two sentences. The first is topological states of matter may provide remarkable robustness. And that robustness, that stability, may be useful for overcoming decoherence and noise in quantum computers by using this idea of topological quantum computation. But point number 2 is topological quantum computation is quantum computation. It ain't going to be easy. That's not a magic way to realize a quantum computer in 5 years. But still, it's a very, well, I tried to convince you that it's a very stimulating field with many new concepts. Thank you very much.
So after we get through the questions and answers, I need 1 more minute of your time. So I think we will consider forming a committee to vote you into the Hall of Computer Scientists, so you get an additional title. Questions, please. Moshe, what a surprise.
There was a National Academies report that came out last year looking at the prospects of quantum computation. And one of the things is you say, okay, what are the prospects of being able to break RSA using quantum computer? And you assume that the keys, let's say, are about 2,000 bits long. And then, okay, so you need 4,000 qubits, and then you need error correction. And so it's actually not unreasonable to think that we'll probably need something like 100,000 qubits to be able to break RSA. Is that something we're going to see in our lifetime?
Could you say that louder?
Not young enough.
So I'll tell you first the optimistic answer. The optimistic answer, which I'm sure you know, is not when I was born, but when my mother was born, my parents were born. There was not a single transistor on Earth. Nowadays, there's more than 1 transistor being produced every second for every human being on the planet.
For every ant.
For every ant, maybe. Okay. So, and that, 3 generations, or 2, actually. So it's very hard to make these kinds of predictions. Try to predict what's going to happen tomorrow. So the lesson, the reason I brought up the transistor is that was an example of an exponential growth, right? Once they figured it out, Bardeen and Shockley and their successors, it went like fire. Will something like that happen in this context? I don't know. It's a very, very challenging endeavor that the physics community, computer science community are taking here. I don't know. It's really hard to say. I wouldn't exclude it. I wouldn't rule it out. I don't think it's completely impossible, but I don't know.
Other questions? Maybe while we look for someone else, I have a question to Charles. You had this sentence that said that you don't think it's worthwhile showing that a useless problem that cannot be done on a classical computer can be done on a quantum computer. Can I challenge the word useless there? I mean, even if the problem is not a practical problem, I think figuring out that there is a problem provably, say, intractable in the classical sense, but can be done in polynomial time on a quantum computer would be a major discovery, which is not the case for factoring because we cannot prove it's intractable. It's really a comment. I mean,
Do I want a microphone? Well, I don't want to embarrass the profession of computer science, but there are no provably intractable problems short of P space. So we don't know that P is not equal to P space.
yeah, but intractable, you know, having an exponential lower bound on time, for example, or on space. I mean, there are such problems.
Well, so it's hard to find. People have different feelings that for factoring is hard is less sure than P not equal 10P. But that's just sort of a gut feeling.
I'm talking about exponential lower bounds. Maybe we do this offline.
So that's not what I was talking about in that issue. I was saying people, this was not a computer science proof. This was a building a quantum computer and showing that it does something that a classical computer can't do in the same time. Is mainly useful. Yeah, with current technology, is mainly useful for trying to convince people that quantum computers couldn't exist in principle, that they're wrong. Well, those people will never be convinced, so it's worthless trying to convince them. Most people believe that quantum mechanics is sound, that there isn't a fundamental obstacle in principle to building a quantum computer, just a terrible engineering problem. Often I compare it to fusion energy. It's not a problem. We know that it can be done, but it's been impractical for many decades and may continue to be. So that's why I say that the effort to prove, they call it quantum supremacy, which is kind of a offensive word in itself. I think the point of all these experiments and the reason for doing them is to improve the understanding of decoherence, improve the understanding of all the things that you do need to know how to do better to make a quantum computer, not to convince people who believe that there never will be a quantum computer. Yeah, so that's what I mean.
Thank you. Any other questions to Adi?
There was over there.
Yeah.
Apart from quantum computing, are there any other uses for these school systems?
Yes, actually, there's one that's almost obvious. So you know, one part in 10 to the 9. So you can use this measurement as a way to standardize the ohm. So you know the standard of the kilogram is some piece of iridium something or other in Paris, in some museum near Paris. And you need to go to Paris every time you want to know what a kilogram is. With the ohm you don't anymore. Actually also with the kilogram you don't anymore. But this allows you to have an experimental kit in your lab which defines the ohm up to 1 part in 10 to the 9. If precision is something that is important to you, then it's a use. Maybe I should have mentioned at some point, these are all low temperature experiments. That means that if you want at home to standardize the ohm, you're not going to use it. It makes it not, rather expensive experiment.